Large language models, or LLMs, are powerful at understanding and generating text. They can answer questions, draft emails, and summarize documents in seconds. But what happens when we ask them to actually do things in the real world? Imagine this request. Can you do it for me? Book a 6 a.m. gym near my home, reschedule my dentist with an Inno network provider, order 10 pounds of grain-free dog food under $40 to arrive by Friday, move Tuesdays 3 p.m., meeting to the next all-handsy free slot, plan a commute that is safe if it rains, and text my partner when it's done while staying within my permissions and budget? Here is why a plain LLM falls short. It has no tools to use by default. It cannot read your calendar, check your insurance network, see the weather, or send a text without integrations. And what's worse, its context is ephemeral. A single prompt and response has no durable state, so long-running tasks break. And third, control over multi-steps work is weak. Complex dependencies, like reschedule, then notify, then update routes, require planning and verification. And finally, reliability is uneven. The model can hallucinate, produce the wrong schema or format, and hit timeouts, so it needs retries, validation, and clear guards for budgets. That's why, instead of relying on a vanilla LLM, you often reach for a workflow, a sequence of deterministic steps that call APIs and services. So in this way, workflows are good at tool using, multi-steps, and longer context. But they show their limits when inputs are messy, goals shift, or you try to hard code every branch, brittleness creeps in. In our planning scenario, a workflow can reschedule a meeting and place an order, but when unexpected events occur, for example, a required attendee of the meeting declines the new time, or the selected item is out of stock, you end up creating new branches, and the workflow quickly becomes brittle. To bridge that gap, we use an agent, a goal-directed loop that plans, uses tools, maintains memory, and adapts. Agents handle ambiguity and evolving sub-goals with feedback while staying within guardrails like budgets. In the daily scenario, the agent coordinates calendars, filters in network dentists, checks weather, adapts when slots disappear, and keeps within budgets. Now, with that decision rule in mind, let's look inside the agent itself. Intuitively, think of the system as modular parts that work together. Perception normalizes inputs and answers what arrived. The reasoning engine, often an LLM, interprets and plans, answering what does it mean? The knowledge base stores facts and embeddings, answering what do we already know? And memory maintains short-term context, answering what have we seen before in this session? And then an action layer calls tools and APIs, answering what can I do now? A planner or policy selects the next move, answering what sequence gets us to the goal. Finally, after multiple iterations, the agent outputs the final answer. What's more, the agent acts in a real, often noisy environment. It observes results, updates internal state memory and knowledge, and adapts plans. So it doesn't run just once. Instead, it operates in a loop. Perceive reason, plan, act, observe, update, and continues until the goal is reached, or a stop condition is met. Of course, choosing the right approach isn't about always preferring agents over LLMs or workflows. It depends on the job to be done. Use a vanilla LLM for bounded, single-shot language tasks. Choose a workflow for deterministic processes with well-structured inputs, and an agent when goals are ambiguous, with multi-step iterations. Pick the smallest, safest system that meets your requirements and operate under explicit permissions, budgets, and validation. Now that we've built an intuitive feel for agents, let's dive deep into the mechanics. How an agent is structured, how each component works, and how they come together in practice. We'll evolve a simple LLM into a complex agent that can use tools, keep state, and adapt to feedback. First, we start with the most basic setup, a single model call. It reads your inputs called context of LLM, the length of any input called the context window. The input usually consists of your system prompt as global rules, and plus the user prompt for this specific instruction, and then produces an answer as a plain text called assistant prompt. There are no tools, And no durable state, just input and output in one shot. Now if the user asks, "Write a message to pump me up for a 6 a.m. gym session tomorrow," the model simply writes a short motivational message. Since the model has no calendar to check and thus to set a reminder, so it won't remind you at tomorrow 6 a.m., just pump you up right now. To bridge that gap, we give the model access to tools. After input, it may rely on external resources called tools or functions. It will send a structured message, usually using JSON format. It has a tool name and some arguments to provide query information. The tool will validate, execute, and return the result. Then the model continues to output the final answer. Imagine the user asks, "What date is next Friday?" and schedule a 6 a.m. gym session. The agent calls a calendar tool to find the date for next Friday, then receives the 31st of October 2025. In order to schedule the gym session, it then uses second tool, Scheduler, to create an event for 6:45 a.m. on that date. After both tools return their results, the agent combines them into a single natural response, such as, "Next Friday is the 31st of October 2025. I've scheduled your gym session from 6 to 6:45 a.m. Beyond your custom-built tools, MCP Model Context Protocol defines a common language that lets agents understand and use external tools in a consistent way. For an agent, this means it can easily discover what tools are available, know exactly how to call them, and even share the same toolset with other agents. It makes tool use more scalable, standardized, and easier to maintain. Now, after learning how the agent uses tools, let's look at a tougher task: move Tuesday's 3 p.m. meeting to the next open time without an all-hands conflict, and text my partner once it's done. You can't do this in a single step. It takes a plan. First, the agent reads the team calendar to find the next suitable time. Then it proposes the new slot to attendees. Once a time is accepted, it updates the event and finally sends the text to confirm. After all these steps, the agent outputs the final answer. The meeting is rescheduled, and the partner has been notified. While it runs, the agent also needs short-term working memory. It includes history and states, like which open time we tried, who accepted or declined, the final event ID, and whether we already sent the SMS. This is private, ephemeral state the program keeps between tool calls, so the model doesn't have to reinfer everything every turn. And here's an important distinction. Working memory isn't the model's input context. The context is what the model can see in one call, like rules, tool schemas, and it's token limited and build. Working memory, by contrast, is your app's own state outside the prompt. You only feed the model what it needs at each time. That keeps prompts light, protects privacy, and makes multi-step control reliable. However, the context window and working memory aren't enough to keep an agent personal and consistent across time. The context window resets every call. Working memory is temporary app state for the current task, not a durable record of a user's preferences. To remember facts and constraints beyond the current interaction, like wake-up times, meal preferences, budget ranges, and insurance constraints, you need long-term storage, called knowledge base. It usually uses a hybrid approach. Keep structured facts, profiles, settings, IDs in a database, and store unstructured, meaning-rich snippets, like notes, messages, as embeddings in a vector database. An embedding is a numeric fingerprint of content that captures its meaning, and a vector database is optimized to quickly find similar fingerprints. Here's the working process. Knowledge base, working memory. Input, context. At runtime, the agent pulls both structured profile facts, for example, a vegetarian meal preference, and the most relevant unstructured snippets from documents, for example, a recent chat note. It activates these as working memory, then includes only what the current input requires in the prompt the context window. These selected facts shape the plan and tool calls, thus output better answers. Of course, during tasks, the agent also summarizes older conversations and writes those condensed insights into the knowledge base for future retrieval. When agents work in real environment, things get messy, like a tool calling times out, a site rate limits, a gym that looked open is actually closed, or a search returns nothing. Instead of stopping, the agent needs to observe the outcome, updates its working memory, and smoothly replans. For example, if a 6 a.m. gym search shows the nearest option is temporarily closed, the agent notes it, tries the next closest choice, then checks in with you before moving on. Overall, the agent flows end-to-end as follows. The orchestrator accepts a user goal as input. The planner decomposes it into steps. And it also retrieves related information from memory, both long-term knowledge base and short-term working memory, to fill the context. Then, the execution engine performs tool calls and aggregates intermediate results. An evaluation and guardrails layer checks, outputs, triggers, retries, or alternate plans when needed. The final answer is synthesized from verified results, and relevant memories are updated for future turns. This modular design keeps components loosely coupled, yet well coordinated, enabling reliable, scalable, and explainable behavior across tasks. Building on the overall loop, there are some popular agent patterns you can choose for different cases. React, reason, act, observe is a solid default for short, tool-using tasks with rapid feedback. Plan and execute first drafts a plan and then runs it with checks. It shines when steps depend on each other. Reflection, sometimes called reflection, has the model review and improve its own output before finalizing. Use it when quality really matters, such as writing or analysis. Chain or tree of thought keeps lightweight reasoning or branches on alternative plans for tough problems. RAG-first agents always ground answers in retrieved documents or facts, ideal for policy, compliance, or private data. And in larger systems, multi-agent setups, split roles, planner, executor, reviewer, when responsibilities are clear and interfaces are stable. With all these pieces in place, you can now build agents that start simple, add tools, and state as needed, and ultimately become mature agents that remember, adapt, and deliver. Now, for the next part, let's focus on the detailed Python code of a minimal agent built from scratch. Roughly speaking, it consists of a minimal agent loop, a tool layer, and an LLM wrapper, so you can inspect, modify, and extend each part without any framework overhead for better learning. The project's skeleton is mainly these files: main, agent, tools, LLM, and .env, file for secrets. Main.py provides two main functions. One is build agent, which creates a new agent with selected LLM provider. Then, registers tools with clear names and descriptions. Second one is a minimal REPL for interactive turns. For each turn, waits user input and calls run turn to produce a reply. And that's all, just wiring. In file, agent.py, during the initialization stage, there is a toolset to hold all tools, functions, and system prompt is set to "You are a helpful assistant" as a global configuration, which you can modify to fit your specific environment. Then it gets a LLM from the argument. Finally, memory, specifically the working memory, will store all state messages, including user, assistant, and tool messages. For each run or turn, the agent prepares input, including the latest user message, along with a compact working memory. It then thinks for a while, optionally calls a single tool if needed, observes the result, and produces its final reply. Overall, the output is either a direct response or a final answer after the tool has run. And you can see, we also append every user, assistant, tool message to the working memory and keep the memory trimmed so that the context stays lean and efficient. In practice, I recommend using the LLM provider's built-in tool or function calling feature if it's supported. It eliminates fragile string parsing, enforces schemas, and reduces hallucinations in tool names or arguments. The file tools.p defines a set of safe, sandbox tools that the agent can use. The calculator performs basic arithmetic safely. File read and write operations are restricted to the sandbox directory for security reasons. The web fetch tool retrieves a web page and returns its title, and the first paragraph. Each tool includes an executable function and a short description. Clear descriptions help the model select the right tool for each task. You can also modify existing tools or add your own custom ones as needed. File.llm.py wraps an LLM endpoint, OpenAI-like, or Ollama, so you can swap providers by changing just one parameter rather than refactoring the agent. For example, in OpenAI Provider, each request has such payload parameters. If you need to use LLM built-in tool calling feature, just provide a list of tools and set tool choice to auto-value. Lastfile.env introduces secrets locally and safely. Put keys like OpenAI, API, key here instead of hard coding. Load them at process start. For example, using load.tenv of python.tenv. Package so code can reference API key by code OpenAI. API key. Meanwhile, add file.env to git ignore file to avoid disclosure. Overall, we built a minimal inspectable agent. Main.py runs the REPL loop. Agent.py orchestrates the prompt, LLM, and memory. Tools. .py provides basic tools like math, file I/O, and web access. .llm.py abstracts model providers, and .env stores secrets. In this part, you'll get production-ready optimization tactics to make your agent fast, cost-efficient, and dependable. We'll cover 4 areas: latency, cost, reliability, and safety. First, let's make it feel instant. When users type, they want feedback right away. So use stream partial responses to show progress while the full answer is still being assembled. Then, wherever possible, use asynchronous I/O independent tool calls run in parallel instead of queuing behind each other for longer time. For repeated flows, prefetch likely resources and keep hot paths warm in a cache so the second and third runs are noticeably faster. Once perceived latency is under control, the next constraint you'll feel is cost, so let's turn to that. 1. Track tokens per request and set practical budgets so you catch cost creep early. 2. Simple tasks like classification, routing, extraction to smaller, cheaper models, and reserve premium models for the few moments that truly need them. 3. Batch requests that naturally groups like embeddings, retrieval, and cache tool results when reuse is safe. 4. When budgets get tight, degrade gracefully. Switch to a smaller model or a summary-only mode that still delivers value. Now, let's make it resilient. Here's the thing. Agents may fail. It's just gonna happen, so you need solid error handling. When you hit temporary errors, like HTTP 429 for too many requests, or 500 for server internal error, add smart retries with some delays. But don't let it retry forever, right? Cap those attempts. Put time limits on every tool and API call so nothing hangs infinitely. And finally, track the important stuff. Speed, errors, costs. Use tracking IDs so you can trace problems and actually see if your fixes are working. Finally, let's talk about safety. Always validate and sanitize inputs before running any tools, especially ones that touch the file system or network. Then, enforce authentication, who you are, and authorization, what you can do, at every boundary. Also, sandbox all file access and code execution to lock down paths and environments. On the other hand, design your tools to be small and single-purpose, so the model can use them safely without unexpected side effects. For secrets like API keys, as mentioned earlier, use environment variables or a proper vault, and make sure they never show up in your logs. Overall, with latency, cost, reliability, and safety working together, you have a production-ready baseline. Since we've been talking about a single agent, what's inside, how it works now, let's make a group of agents work together and see what happens. You'll see how a small team of simple agents can collaborate, how they share memory without making a mess, and how to keep quality high as the system grows. First question: why multiple agents? The short answer is focus. When each agent has one clear job, prompts stay simple, context stays small, and it is easier to see where something went wrong. To coordinate them, we use a hub and spoke setup. A single coordinator called hub orchestrates workers called spoke who read, write a small shared memory bus. It's the default and easiest to debug. In our weekly planning scenario, the coordinator acts as the hub giving out tasks, while specialized agents work as spokes. A scheduler handles calendar and constraints. A router handles weather and commute. A shopper handles ordering, and a notifier handles messages. Now the coordinator receives a user input and sketches a simple plan, then distributes small subtasks to the right agents. The scheduler is asked to reschedule the dentist appointment with an in-network provider. The router is asked to check the forecast and, if there is heavy rain, to suggest an indoor option or adjust the commute. The shopper is asked to order grain-free dog food for under $40 with delivery by Friday. The notifier is asked to send a confirmation message once all tasks are complete. Each agent writes a short and structured record into shared memory. Each one should be tagged with metadata, such as which agent wrote it, what operation was performed, when it happened, and which topic or task it belongs to. Finally, the coordinator then reads the shared memory, looks for gaps, and sends quick follow-ups if needed. When all criteria are met, the coordinator posts the final reply to the user. So this workflow we saw is just one way to organize multiple agents, called orchestrator with workers pattern. Next one is the router with specialists pattern. A router looks at each task and forwards it to the proper agent. For example, simple tasks are forwarded to a cheap and fast agent with a small model, while difficult tasks are forwarded to an expensive and slow agent with a large model. So this pattern gives you fine control over cost and speed. Third, the supervisor with critic pattern. One agent called worker does the work and proposes a solution, while another agent called critic checks it against a checklist or criteria and gives explicit revision feedback. And a supervisor controls the iteration loop to avoid infinite review cycles. Fourth, the hierarchical planner pattern. A high-level planner decomposes the goal into a plan, producing a sequence of smaller steps, each assigned to a specific agent for execution. And when new information comes in, continuously revises or fully regenerates the plan, ensuring the system adapts dynamically rather than rigidly following the initial blueprint. Here are common multi-agent patterns. The key is to pick one pattern per workflow and keep things simple. And in summary, now you have a clear path to grow from a single agent into a small team. You can define clean roles, use shared memory, keep orchestration simple, and maintain high quality while scaling things up. Congrats! You've gone from understanding why agents exist beyond plain LLMs to shipping a dependable tool-using system in production. We drew the line between LLMs, workflows, and agents, then introduced the core loop, input, plan, act with tools, observe, and output, and other modular pieces, working memory, and a knowledge base. We implemented a minimal inspectable agent, REPL, without any framework. Then we talked some advanced topics, improving with streaming and async, routing and caching, and reliability guardrails. We scaled the design with multi-agent patterns, using shared memory and instrumentation. You now have the judgment to choose the right approach, runnable code, and the practices to operate it with confidence. And there are other advanced topics to explore. Start with reinforcement learning for agents. Use reward signals from tool feedback and human feedback to improve. Add multimodal capability so your agent can see and hear. Vision for documents and screens. Audio for hands-free interaction. To specialize the model, fine-tune on your own domain data to improve performance. Okay, this video is about to end. If this video helped you build your foundation, subscribe so you don't miss the deep dives coming next. And thanks for watching. See you in the next episode.